In this video, we're going to introduce the concept of distance in the context of the analysis of high throughput data. Clustering is a methodology that requires us to define distance. Clustering is something that we do, and implicitly or explicitly we use distance to do it. For example, when we cluster animals into groups, in a way, we're defining a distance. We're saying which animals are closer to each other and which animals are further away from each other. If you read the genomics literature, you'll have seen heat maps such as this one. In a heat map, you can see on the left and the top, you can see that there's a dendrogram, and these are created using clustering. Therefore, we need to define distances between both rows and columns of the data matrix. So let's start with just a simple definition of distance. This is just Euclidean distance. If you have 2 points in Euclidean space, we know how to compute the distance. We subtract the difference in the x-axis, the difference in the y-axis, square them, add them, and take the square root. Now, in high-dimensional data, we can't really do that because points are not two-dimensional. Here's an example of a data set that we have been looking at, and this is just the first 10 rows and 5 columns of a data set that includes gene expression measurements for thousands of genes on dozens of samples. So to be able to talk about distance in this context, the first thing we have to do is define what a point is. We no longer have 2 points in space or in a Cartesian plane. Instead, we have these, in the case of samples, we have these long vectors that are 22,000 plus numbers long. Now, once we know what a point is, then we'll have to define what distance means for 2 samples or 2 columns, and what distance means between 2 features or 2 rows. In the case of this data set, they're genes. All right, so a point. So a sample is simply a point in this case, 22,215 dimensional space. Every gene gets a number, and all these numbers together define a point for a sample. In the case of features or genes, because this data set has 189 columns, that's the number of dimensions we have for each feature. And once we've defined points, then we basically use the same definition that we use for 2 dimensions. We take the sum of the differences squared and then take the square root as shown in this formula for samples I and j. So here, as an example, is the distance between the 3rd and the 7th column. So you can see in the formula, we're simply taking the 3rd column and the 7th column and applying the formula that we just showed. For the rows, it's the same definition. Instead now, we add across the samples. For each sample, we take the difference between the 2 genes, square it, add them, take the square root. So here's that formula applied to the row 5,124 and the row 11,924. All right. So one last little bit of math. Using what we learned in the second course, we can define distance, squared in this case, using the sum of squares. That's what we do to compute distance between the difference between the columns. So you can see here the cross product between the difference between 2 columns defines the distance squared between those 2 columns. So this is a mathematical approach that we can use to compute distances very quickly. And we'll see that going forward.